Ibuprofen, Its Effect on Prostaglandins by Karen Busby, Mike Mirza, Bridget Verbeck, and Anna Warzeka. Ibuprofen. Ibuprofen is a non-steroidal anti-inflammatory drug that inhibits prostaglandin synthesis. By doing so, it can reduce fever, pain, and inflammation. Prostaglandins. Prostaglandins are molecules that are formed in response to tissue trauma. Excess prostaglandins synthesis can cause prostate tumors, arthritis, pain, and inflammation. By inhibiting the synthesis of prostaglandins, ibuprofen is able to alleviate these symptoms. Synthesis of prostaglandins. This is a simplified Marvin sketch of the overall prostaglandin synthesis. The bonds highlighted in yellow are the bonds that are formed during the reaction, and the bonds highlighted in green are broken during the reaction. A more detailed explanation will be presented later. Cyclooxygenase activation. The prostaglandin G2 product presented in the previous slide is formed through a cyclooxygenase reaction. This reaction follows a radical cyclic mechanism. The step presented here is the formation of a tyrosyl radical. This radical is the initiator of the cyclooxygenase reaction. The tyrosyl radical is formed when tyrosine 385 donates an electron to the ferryl species formed by the ferric heme contained within the COX enzyme. Cyclooxygenase reaction. The tyrosyl radical formed in the previous step is now able to react with arachidonic acid, the substrate of the COX enzyme. The radical highlighted in green reacts with the wedged hydrogen atom attached to carbon 13. This hydrogen atom is a pro-S atom, and therefore the final prostaglandin G2 product exhibits an R stereocenter. A double bond is then formed between carbon 12 and 13. This leaves a radical on carbon 11, which is highlighted in blue. A molecule of oxygen then reacts with this radical, forming the third structure, and a radical highlighted in orange on one of the oxygen atoms. The radical then reacts with carbon 9, causing the double bond between carbon 8 and 9 to break. The radical is transferred to carbon 8, which is highlighted in red. This radical reacts with carbon 12, forming the base of the 5-membered ring, breaking the double bond between carbon 12 and 13. The radical is now on carbon 13, which is highlighted in purple. The next step involves this radical reacting with a molecule of oxygen, forming the radical highlighted in yellow. The tyrosine 385 then transfers a hydrogen atom to the oxy radical highlighted in yellow. This final step produces prostaglandin G2, and it regenerates the tyrosyl radical, which is now able to again initiate the cyclic reaction using another molecule of arachidonic acid. Active site of COX. The active site of COX is best illustrated by this JMOL view that illustrates the interactions between arachidonic acid and the various residues of the COX enzyme. Competitive binding of ibuprofen to the active site causes inhibition of the COX enzyme. Ibuprofen binds to the active site of COX by hydrogen binding to the tyrosine and arginine residues. However, no reaction occurs between the COX enzyme and ibuprofen because the structure of ibuprofen is different than that of arachidonic acid. This allows ibuprofen to effectively inhibit the action of COX by preventing arachidonic acid from binding to the active site. Without the ability to bind to the active site, arachidonic acid cannot undergo cyclooxygenase reaction, and thus no prostaglandins are synthesized. Inhibition. Ibuprofen is able to act as an inhibitor to the COX enzyme because of its similarities in structure to arachidonic acid. These similarities are best shown in this JMOL comparison of the two structures. Ibuprofen is one of the most commonly used over-the-counter pain-relieving drugs on the market. The COX inhibition pathway is important to pharmaceutical research in the development of future drugs that hold the potential to alleviate various symptoms which are caused by excess prostaglandin synthesis.